I'm just waiting for the recording to start. Okay. So, Assalamu alaikum wa rahmatullahi wa barakatuh once again. Today we are going to start the second session of Advanced RC Design. In the previous session, we have taken a recap of whatever you have studied in Design of Structures 1, in Materials and Methods of construction, a recap of the basic properties of concrete and steel, the different structural elements, the different structural systems, and accordingly, we are prepared now for the second session. Okay. Now, the second session is going to talk about the structural design procedure. Okay. Unfortunately, I didn't upload for you the PowerPoint because I just finished it. Okay. I tried my best to modify. It's the same content, but I tried my best that it's going to be more visual, so you will be able to understand and visualize. It's a very important thing that you will be able to imagine and visualize the things. Okay. So the chapter is called Structural Design Procedure, and once again, this is an introductory session for the actual Advanced RC Design. Okay. Actual Advanced RC Design will be starting from the design of solid slabs, design of two-way solid slabs. Before doing that, we need to know certain particular things. One is a recap of whatever you have studied. Second thing is the structural design procedure. So our journey is going to be a little bit easier whenever we are starting the actual designing. Whatever is going to be covered today is going to be about the different procedures. So the procedure normally starts with development of of architectural and structural drawings, which we have discussed slightly in the last session. And then the second step is going to be idealization of the structure into frames and elements, whatever you have studied as a free body diagram. And then we are going to see the next step, which is going to be analysis using either structural software packages or manual. In our case, for the course, we are going to go for manual. Or you have studied the analysis in your theory of structures 1, theory of structures 2. Some basic analysis can be done using the code as well, which we are going to use and do. The last step is going to be designing. Okay, so once again, the whole journey of designing any structural element starts with you having the drawing. After having the drawings, you need to do the idealization. Idealization involves involves two things. One is drawing it into simple shapes, whatever you know as free body diagram, and applying the corresponding load. Okay. After you have your drawing, the basic free body diagram with the loading, then you will be able to start doing the analysis according to the type of that particular element. Okay. And then finally, whenever you get your internal forces, you will be able to design. So once again, it starts with the drawing. Without a drawing, I cannot draw the free body diagram. Without the free body diagram and the loading, I cannot do the analysis, getting the shear force and bending moment. And then if I don't have the shear force, bending moment, deflection, I cannot go and design my elements. Are we clear about the structural procedure? Are we clear about the structural design procedure? Any question? Okay. So the first part is going to be the development of architectural and structural drawing. Normally, this part is the duty of the architectural engineer, but the structural engineer is the person who will overview and confirm and check the structural drawing, especially the positioning of columns. So it's very important for you to know how to do the positioning of columns. In the previous semesters, I used to give the students some basics of positioning of columns, but due to the short semester, you can try yourself learning how to do the positioning of columns. Okay, so first thing, we need to bring our architectural and structural drawings, and you can see I try to bring almost the same drawings, and you can see that they are reflecting each other. So whenever we are having a position of a column here, for example, then it reflects here as well. And what you can notice, one thing that you can notice, there are extra beams which are not available in certain places. Like for example, here you can see that we don't have walls, or there is no wall here, but whatever is reflecting in the structural drawing that you have a wall or you have a beam here. Okay.
Mister, we can't see anything.
You cannot see. Okay. Now are you able to see? Now are you able to see? Is it fine now?
Yes, Mister.
No.
No, for me still.
Yes. Some are saying yes, some are saying no. Okay. Those who are unable to see, I'll just try to unshare and share once again. If not, you just go
Now it's
outside and then
okay.
return. Now is it fine with everyone?
Fine for me.
Others, are you able to see? Others, are you able to see? Okay. So as we said, I'll just recap. Okay. So we said different contents are there. We started with the drawing. After the drawings, we said free body diagram and idealization. Idealization includes the free body diagram and the loading. After that, we said we are going to go for the analysis, and then finally we are going to go for the design. Today I'm going to highlight for you the more into software. Whatever we are going to tackle in the course is going to be more in manual design, but wherever we are going to do a manual design, we are going to compare it with a software as well to confirm that our results are going to be correct. Okay. So now if you see here, the first step, as we said, is development of architectural and structural drawings. Now if you can see here, we have the architectural drawing on the left side and we have the structural drawing on the right side, right? We said for the architectural drawing, we are having secondary elements which are not mainly for structural purposes. Now, if you can see, we have doors, we have furniture, we have windows. So these are non-structural elements which will appear in the architectural drawing. Is this clear? Are we clear with that concept? Okay. Now,
Yes.
if you see in the structural drawing, we don't have anything except for the primary elements, which are your column, beam, slab, foundation, structural wall, or shear wall, if there are any. Can you see your structural drawing? Okay. So once again, the duty of making the drawings will be going to the architect. The architect will do the preliminary drawings. Before he starts the final drawings, he needs to go to the structural engineer, where the structural engineer is going to confirm for him the positioning of columns. So the initial positioning of columns will be done by the architect himself, who will confirm, who will verify. That's going to be the duty of the structural engineer. Now, normally, if you say, we provide the beams wherever there are walls. So, for example, here, if you see, wherever there are walls, because we don't want the load of the blocks or the load of the wall to go directly on the slab. We want it to go on the beam, so the beam will be taking the load of the wall. It's very dangerous. It's very critical when you load your slab with the wall directly. It will act as a very huge linear load. Now, in the other places, you can see wherever we have a wall, wherever we are having a wall, there will be a beam. Can you just see that? Wherever we are having a wall here, like for example here, we are having a beam. Can you relate that? Can you see?
Yes.
Okay, so clear thing that you should understand that whenever, or the basic thing when you want to try your structural drawing, first follow the rules. Whenever we are trying to follow the rules, like for example here, if we see, can you see that this is walls, or these are walls? Can you see? Can you see what I have drawn?
Yes, Mr.
Okay.
Yes.
And then can you see that this is another wall?
Yeah.
And then can you see that there is another wall here? And then another wall here. Now you can see here, I don't know whether it's clear or not, but this says for you that this is going to be T and T. This is going to be toilet and bath. Okay, so whenever there is a toilet, normally we separate the slab, because this slab is going to be as a sunken slab. And we are going to learn what's the meaning of a sunken slab. Okay. Now can you see, if you keep following the walls, it will give you the shape of the beams, and later on it will give you the shape of the slabs as well. And whenever there is, like see here, we have a beam, but we don't have a wall here. Can you see? We don't have a wall. Now one thing normally in structural design and structural analysis, normally we prefer to keep the frames going in the same, or going fully from the beginning till the end. Plus this particular slab, the designer at that time, he might consider it to be big. Okay, so he placed, you can place here a beam. It's not necessary for you to place a beam here, but if you want to do, you can do it. Once again, positioning of beams, positioning of columns is going to have different views from one designer to another designer. So if you didn't put a beam in this particular location, it does not mean that your design is wrong. Are we okay? But it means that that slab is going to be huge. It means that your reinforcement for that slab is going to be too much as well. Are we fine? Is it clear?
Yes, Mr.
Okay. The same thing goes for the other walls. You can see whenever we are having walls, we are having beams. And after you are having your beams, you can start doing the positioning of columns. So for example, you can see there is one column here, there is one column, there is one column, and there is one column. You can see now what happens here. If I take this particular portion, you will see that this particular portion is acting like this. Do you agree? Do you agree that this particular portion which I have drawn is represented here? Yes, no?
Yes.
Okay. So now you can see the basic positioning of columns is going to be here, one column, and then we have another column here. Now we can have a column here, we can have another column here, but the distance between the first column to the second column is going to be very close, so it's not preferable to make the column. So where we are going to make the columns, we are going to make them here. Is it clear? Is it clear that this particular point and this particular point are very close? That's why we are not putting the columns close to each other. Are we okay with that?
Yes.
Okay. So this is the basic function. You can do either by following, you can do the beams and columns either by following the walls. Whenever there is a wall, there is a beam. Wherever there is a sunken slab, you need to separate it, so there will be beams. Whenever you have the beams layout, it's going to be easier for you to go for the columns, or you can follow the grid lines as well. Okay, you can follow the grid lines. So wherever we have a grid line intersection, we can have a column position. So if you see here, For example, this is an intersection between A and 1. Can you see that this is A and this is 1? Whenever there is an intersection, we are going to do, unless it's very close to each other. Okay. So that's another method of having your column position. Is it clear? Do you have any question regarding column positioning? So once again, column positioning does not give you always the same result between one designer to another designer. The only thing that the designer or the person who is doing the drawing, he should have a clear logic of why he has put this thing here and why he has not put it somewhere else. Are we clear? Okay. So we said you need to follow the rules. The other thing, you need to be careful wherever there is sunken, wherever there is water requirements. Let's say water requirements means toilet, bath, kitchen. These areas they require water. Whenever they require water, it means that that slab is going to be a sunken slab. Now, how would you know a sunken slab? Can anybody tell me what's a sunken slab? Have you studied sunken slab? Do you know what's the meaning of sunken slab? What's the meaning of sunk first? What's the meaning of sunk? Sunk in English? Any person? To sunk something? Okay. Once again, to
Depth
sunk
will
something.
be, Mr.
Depth will be
Depth
what?
will be different than other slabs.
Okay. Now, do we have for the first thing deep, because pipes go under the slab? No, pipes will not go under the slab. It's not possible that pipes will go under the slab. But one thing to be taken into account: do we have first the same depth for each and every slab, or the different depth? Are we having the same depth or different depth?
Different.
Different. Okay. Now, just to keep it
Also for
clear.
the pipes.
Okay. I'm not talking about the sunken slab. I'm talking about the other slabs now. Do they have the same depth, different depth? Anybody?
Different.
Okay, different depth. Now, let's just say that for example, I'm having one room here. Okay, I'm having one room. And let's say that there's some kind of toilet here. Okay. The drawing is not to the scale, but anyhow, that's just to illustrate that this is the room and this is the toilet. Now, what happens whenever we see it in reality? We see that the finishing level for this room is the same as the finishing level of the toilet. Do you agree? The finishing level.
No, Mr.
The finishing level I'm talking. Do you have your toilet going down or up from your room?
Yeah, same level.
Same level, right? So you have in most of the cases, especially in modern construction, okay, you have it normally same, or as Rashid said, because of the drainage, if you want the water to go to drain, yeah. Okay, but normally it is almost the same level. Now, what happens here? Whenever we are trying to have the toilet slab, now we have tiles here. Let's say that these are tiles, and then after the tiles, we are having some kind of mortar. Okay, and then we have directly our slab. Okay, we have directly our slab. Okay. Now, when it comes to the toilet, it's not the scenario. When it comes to the toilet, we require to have pipes. Wherever there is a water connection, you need to have the pipes. So the pipes needs to be installed somewhere here. So we have the tiles as well, and then we have the mortar as well. But we have our pipes. Now what happens here? I cannot install the pipes inside the slab. Okay. Otherwise, if there is any problem, if there is any leakage, you will have to break your slab. So what we are trying to do, we are trying to lower our slab to a new level. Okay, we are lowering our slab to a new level, the slab of the toilet. Now what happened? We sunk means lowering, means keeping it down. So we are lowering the level of the toilet. Okay. So we have different levels now. Are we okay? Okay. So we have different levels. So this is the slab or the room slab, and this is whatever we call it, the toilet slab. The finishing level at the end is going to be the same. Okay. This is called sunken slab because it's sunk or lowered. Are we fine? Is it clear? Are we clear?
Yes, Mr.
Are we? Okay. Further, when we are going to come up with the design of slabs, we are going to see real pictures and illustrate sunken slabs. Hopefully, if there is time, we will try to arrange for you a site visit where you are going to see these things in reality. Okay. How would I know a sunken slab from the structural drawing? Is it shown in the structural drawing? Any person? Do we normally show the sunken slab that this slab is lower? Is it important to show it? How the person who is working as a contractor, how would he know that this is sunk? Okay, so normally we are showing it using hatch. Okay, as Martin said. Now, if we are showing it using hatch, why it's not shown here? We have toilet and bath here, right? This is toilet and bath. Why we didn't have a hatch here? This is which level? First, this is which level? We are talking about which level now?
Ground level.
Okay, ground level. Now, your ground level slab or your ground floor, is it suspended? Suspended means nothing is supporting it from behind. Okay, now can you see to your roof? Is there anything holding the slab other than the beam and the columns? It is suspended, right?
Yes.
In the floor, in the roof, it's suspended. In the floor, in the ground floor, is it suspended as well, or is it supported by soil? Ground floor. Okay, ground floor is supported by soil. That's why normally we does not include. Okay, we do not include our ground floor or whatever we call it, slab on grade, in the design. Normally, slab on grade is going to have a mesh only, a typical reinforcement. It's not designed. Why? Because normally the load will be taken directly to the soil. the slab does not need to take the load to be transferred to something else, to another element. Directly the slab is transferring the load to the soil. It means we don't need to provide huge reinforcement to resist the bending or deflection happening in slab. Then, the slab is not going to have huge and big deflection in the big moment. Since it's already supported by soil. Are we clear about that? So whenever you see a person who is modeling in reality and he's trying to design a full building, you will see that the ground slab is not going to be shown. He will only be showing your blunt beams. Why he will show the blunt beam? Because the blunt beams are going to carry your walls. So it's very important to show them and design them. Are we clear? Are we clear about this point? Why don't we include the the slab on grade in the design? And that's why you cannot see a hatch here. Let me see if I can show you. If I can show you a picture. This is the slab on grade. Can you see the grade slab or slab on grade? Can you see? Can you see that the reinforcement and the whole slab is laying on soil? Can you see it? So it means directly the slab load will be carried by the soil. Are we okay? Is it clear from the picture here? You can see the reinforcement. We do not provide huge reinforcement. We only provide mesh. Mesh is to stop cracking from happening. Are we okay? Are we fine with that? Okay. Now, if we go to the other level, now if we go to the first floor, are we seeing our are the slabs suspended for the first floor? Your roof, is it suspended? Do you have soil beneath the slab? Do you need to design the slabs here in case of a roof? In case of a first floor or the roof of the ground? Do you need to design it? Is it suspended? Is it supported by soil? Yes? What do you think? Okay, it's going to be suspended. If it's suspended, means the load will be there. It is going to bend, it's going to deflect. So in order to solve the problem of bending and deflection, we need to provide the appropriate reinforcement. In order to provide the appropriate reinforcement, you need to design it. Okay, that's why we design the floor. We design the first floor, second floor, and it goes on. We don't design the ground floor unless it's a basement. Okay, unless it's a basement. Okay. Now, can you see the hatch here? Can you see the hatch in the structural drawing? Can we see the hatch here in the structural drawing?
Sir, can you zoom it, please?
You cannot see the hatch?
No.
Now, are you able to see the hatch? The color here, are you able to see? Are you able to see them?
Yes, Mr.
Okay, so these are the areas, or these are the slabs which require water connection. Okay. Now, the same thing goes to the other floor. So what I tried to bring for you the different floors so you can understand the slab on grade, the suspended slab. When do we design this one? When the slab is not required to be designed as well. Okay. So after you have your drawing, which was created by the architect and then verified by you, you have checked the positioning of columns. You have provided the places where they require water connection or services. Okay. The next step is going to start doing your idealization. Okay. You are starting to do the idealization when it comes to manual design. Now, when it comes to software design, do I need to make the idealization? Do I need to draw the free body diagram if I'm going to use the software? Once again, when I'm going to use a software for the structural design, do I need to still draw my free body diagram? Why do we normally draw our free body diagram? We draw our free body diagram to make the analysis simpler, right? We are trying to remove any 3D things to 2D, which are simple to be understood. Okay. Now, when it comes to the structural software, already the drawings are available in 3D, and the software is analyzing it as 3D, so you don't require to go and draw the free body diagram once again. Okay. Are we clear? But when it comes to manual design or manual analysis or how we are going to do it in this particular course, it's very important for you to know how to idealize. Okay. Like for example, if we are trying to take this particular beam, can we see this beam? Now, if we are trying to design this particular beam, how would you do? First, we need to draw the free body diagram, right? So if I try to draw the free body diagram, this is my beam. There is one support here, so I'm just going to draw the support here, and then there is another column here, so I'm going to supply another support. There is another column here, so I'm going to supply another support, and then I'm going to supply another support for here. Now, what do we have here? What do we have in this junction? Can you see? What do we have in this junction? What is there? Is it a column? Is it a column?
No.
That's beam on a beam, right? That's beam on a beam. Do you agree that's beam on a beam? Okay, so it's going to be a beam on a beam. Now, to how to analyze this particular thing. If I try to take this particular beam, this is my beam. This beam is carried by this beam, by the other beam here. If we say that this is beam number 1, this is beam number 2, this is beam number 3, then my beam number 1 is having beam number 2 as a support from one side and having beam number 3 as a support from the other side. So whatever we have learned that beams can be supported by columns, beams can be supported by beams as well. Okay, so once again in this scenario, beam number 1 is supported from one side by beam number 2, and then on the other side it's supported by beam number 3. Are we okay? So now you can see that this turns to be a simply supported beam or partially fixed beam. Okay, are we fine? Now, in this junction, B1 is acting as a support or is it acting as a load? If this big beam is called, for example, B capital. Now, beam number 1 is acting as a load or reaction or a support. Is it a support or is it a load on B capital? Okay, it's acting as a load. Which type of load? Is it the point load? Is it the UDL? What type of load? The beam is available all over the B capital beam, or is it only available at certain position? Okay, so it acts as a point load. So now what we are going to have when we try to do the free body diagram, we are going to have a point load coming from beam number 1. Okay, is it clear how to do the free body diagram or the idealization? Are we okay with that? Are we okay with the idealization? Now, can we try to do the idealization for this slab? Can we try to draw the idealization for this slab? Or let's have it in somewhere else. Let's have this particular slide. Okay. Now I want to draw the bending moment for this slab. Can you tell me how would you do it? Because that's going to be our next step. Let us take this particular joint. Okay. Now, if I try to draw the free body diagram for these slabs which are available in this region, I need first to draw a different thing. So I need to understand the concept of one-way and two-way slabs. Now, when I say one-way slab, what does it mean? One-way slab is having how many bendings? Or it bends in how many directions? One-way slab?
Nothing extra.
One-way slab bends in how many directions? In one direction. Two-way slab?
Two direction.
Okay. So according to you, whatever you are telling me now, you are telling me that a one-way slab is bending in one direction. Two-way slab is bending in two directions. Do you agree? All of you are agreeing with this thing? All of you agree? Anybody who is having a different opinion? Now it's your time to ask in the introductory session. Later on, we will not have a time to ask basic questions. Okay. Now, if you are saying one way is having only one reinforcement, and then two way is having two reinforcements. Now, in one way, how many direction of reinforcement we have? One or two? Do you agree that this is how the reinforcement will look in its lab? Do you agree that this is how the reinforcement will look? It looks like a mesh. In both, in one way and in two way, right? In both, in one way and two way, it is going to be a mesh. Okay, two side reinforcement. Okay. Now what we know, the basic equation of AS says that AS is equal to M 0.95 Fy into Z. This is the basic equation you have studied in design of structures 1. Now, my argument says that if you are telling me that here you have only one bending moment or one bending in one way slab, it means that you have one M, it means that you have one AS. If you are having one AS, then why would you provide two direction reinforcement? Anybody? Once again, you said in one-way slab it bends in one direction. It means there's no bending in the other direction. If there is no bending in the other direction, it means M is 0. If M is 0, then your AS is 0. If your AS is 0, then why would you provide second direction reinforcement? Since it bends in one direction, we have provided one reinforcement to stop or to resist the bending in that direction. And then if it's bending in the other direction, then we provide another reinforcement in the other direction. Now, when we say one-way slab and we say two-way slab, it does not mean that we have only one moment or one bending and then two bending. One way is referring that we have one major bending moment and one minor bending moment. It bends in both directions, but we have only one major bending moment in one direction. Okay? It means two reinforcements will be there. One reinforcement will resist the major bending moment, which needs to be designed for. And the other one you use to calculate it as whatever you call it as secondary or transverse reinforcement, in which you have provided the minimum reinforcement because we have a minor bending in the other direction. Okay, so one way bends in two directions, but one is major, one is minor. The major needs to be designed for, the minor you don't need because the minimum is going to be sufficient. In two way, it bends in both directions. Okay, in two way, it bends in two directions. It means that you need to calculate the bending moment not once, you need to calculate it twice for both directions. Are we clear about this point? Are we clear about this point? Okay. Now, if we try to draw the free body diagram for this particular slabs or these particular slabs, and you can see now one-way slab normally is bending in the short direction or long direction, along the short or along the long direction. One-way slab, short direction. We said one major bending. Is it bending on the short? Are you calculating for the short direction or are you taking long direction into account? When you have designed, so you are taking into account the short, and we are going to elaborate on that whenever we are going to come to the slab design. Now, just to summarize or just to give a brief about this particular case, now you can see that this is a one-way, this is a two-way, this is a two-way, and this is going to be turning to be a one-way from the shape. Okay. Now, if this is a one-way, then it bends in this direction, which is short. If this is a one-way, then it bends in the short, which is here. This is a two-way, so it bends in both directions, here and here. This is a two-way, so it bends in two directions, so here and here. So if I want to take a strip, here, then I can draw my slab as this, where this is, let's say, slab number 1, this is slab number 2, and this is going to be slab number 3. So slab number 1 is supported by, let's say, supported by a beam here. So I have a beam. Slab is always supported by beam. Beam is supported by either column or a beam. Okay. Slab number 2, this is the other or second support for slab number 1. Okay. So let's say that this is reaction number 1. This is reaction number 2. Reaction number 1 is taking this side, or it's taking half of S1. The other beam is taking half of S1 and then half of S2. Okay, so this is reaction number 2, and then we have another reaction here, and then we have another reaction here. Okay, so this is going to be where is S1, which is here, and then we have S2, and then we have finally S3. Are we clear? Are we clear on how to draw the free body diagram for the slab? So the same concept, the only thing that you need to understand the one way and two way. And later on, if you know how to draw the free body diagram, it's going to be easy for you to draw the bending moment diagram and accordingly design your slab. Okay. Okay. I'm going to draw a strip directly inside, so you will understand. So if I want to draw the bending moment diagram in this particular line, okay, which is serving three slabs, S1, S2, and then S3. How many supports are there? You can see that we have support number 1, we have support number 2, we have support number 3, and then we have support number 4. If I want to idealize it, then I'm going to draw it here. Support number 1 is going to be having a reaction. Support number 2, another reaction. So this is slab number 1. And then we have slab number 2 with this particular support. And then finally we have slab number 3 support. Okay. Once again here, 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 and then here. Is it clear? Are we okay now? Once again, it's very important for you to idealize. If you know idealize, designing a slab shouldn't be a big issue for you. Are we okay? Further idealization and further cases will be taken whenever we start the actual designing of slabs. Is it clear now how to do the idealization for the slab? Okay. Now going for the third. Okay, going for the third. Going for the third, and once again different slabs are here. Okay, different slabs are here. Now if you can see, this is, if we are trying to zoom here, this is a single slab. It tends to be a one way. Now for your case, you need to verify it's one way or two way by getting the ratio. But anyhow, from the look, it looks like a one way, means it bends in one direction. If it's bending in one direction, this is my short. If I try to draw the free body diagram, then we have it supported here and we have it supported here. So this is going to be my idealization of this slab. Are we fine? Are we okay with the idealization? Okay. So after idealization, the next step is going to be second part, wherever we are going to have the loading. Okay, wherever we are going to have loading, or before I wanted to try to show you the idealization using software, how it will look like. Now, as you see, I tried to model here. Okay. So I took these beams and wanted to show the idealization. Okay, so can you see now the idealization? It turns the 3D into 2D. And now, can you see here? Can you just concentrate? Now, what's happening? This particular beam, the whole beam, is supported by 4 supports. So 1, 2, 3, 4, but we have something here in the middle. Can you see this one? This is representing a beam sitting on this long beam. Okay, so this is beam on a beam interaction, or beam on a beam joint. So if we go and see it here, now you can see we have, okay, before doing that, Just 1 second. Okay. Now, if you see this beam is supported by support number 1, and then we have number 2, 3, and then there is number 4, which is the column here. Okay. So 1, 2, 3, and then we have 4. Column number 1, column number 2, column number 3, and there is column number 4. So it's supported by 4 supports, but we have a beam junction, which is going to be shown here. Now, can you see that this is the beam interacting with the acting as a point load now? Can you see that there are 4 columns, 1, 2, 3, 4, and this is the point load acting on this beam? Okay. Now, just to illustrate for you a column, this is going to be a column. This is the idealization of a column. Idealization means trying to shift it from a 3D to a 2D into into a simple drawing that we can understand and analyze. Okay. And this is how you will do the idealization for a frame. Okay. This is what you used to do in theory of structures 2. Before you start, or theory of structures 1, before you start your analysis, first you need to transfer whatever 3D into a 2D frame. This is the meaning of idealization. Are we clear? Are we clear about the idealization? But once again, as I told you, idealization when it comes to software is not important, because the software will do the job for you. Why do we do it for manual designing? We do it for the simplification, so we can understand whatever we are trying to analyze manually. Are we fine? Are we okay? Now, after you have your idealization and your drawings, the next step is going to be the loading. Now, in most of the cases, while you have studied theory of structures 1 or design of structures 1 or theory 2 or design 2, the loading used to be given to you. Now, that's not the case when it comes to reality. Okay. The case that you need to calculate your loading. Okay. And loading can be calculated depending on its nature. So we have 2 types here. One is representing the weight of building or weight of building material, that's representing the dead load. And then the other scenario, which is life load. So we have 2 different codes. I have already uploaded for you these codes, and you can refer to them. Okay. So if you can see here, when it comes to weight of building materials, so it will open. Okay. So now if you see, this is the weights of building materials code. Different things are there. The most important thing that you should identify already, what are the materials to be used. And you can see for each and every material, there will be the mass of that material or the density depending on the requirement. So for example, if we are talking about concrete, for example, if we can search directly for concrete. From there you will know how much is the value of the concrete. Okay. So you can see that natural aggregate concrete is around 2,307 kilogram per meter cube, which we are taking as around 2,400 kilogram per meter cube. So for each and every element, okay. So for each and every element, you will be having its either density or area loading. Like here, you can see it's per meter cube, means you need to have the thickness. That's why we multiply, in order for us to calculate the self weight, we multiply it by the thickness of the slab. And we will learn why we are multiplying by the thickness, why not the length or the width later. Okay. Now you can see here the unit is a meter square, so it's already ready to be loaded in a slab. Okay. You cannot load a slab unless it's per meter square, and we are going to learn why. But the most important thing, whatever loading when it comes to finishes or dead load, it should be generated from here. Okay. So each and every material is available. So when it comes to your assignment, when it comes to even your classes and whatever, we are going to get the values from here. Okay. All the values are going to be generated from the codes directly, and you should know how to use these particular codes. This code is from 1964, I think. This is from 1964 and still now used. Okay, because normally the weights of materials will not change. And then the other one is loading for buildings, which is representing a life load. So if we go and see here, okay, so this is loading, the loading or the life loading. Okay. Now you can see when it comes to life load that we have different categories. We have different categories. So first category says for you domestic and residential activities. So for example, if you are designing a villa, that should go for the category of A. Now, whenever we are talking about like regular rooms, then it's going to be 1.5 kilonewton per meter square. Bedrooms are going to be 1.5. Hotels, if we are talking about bedrooms in hotels and motels, it is going to be 2. And it goes on. For each and every type of room, they have given you the life loading. And when it comes to reality, we don't have different loading. I'll not go and load my toilet to be 2, for example, and my life load for the room is going to be 1.5. That's not practical when it comes to reality and your work later. Later, we are going to have only one life load, which is going to be the highest, unless you have very huge differences. Like, for example, I have 2 and then 4. Like, for example, the life load for a staircase is taken as 4. So I load all the other slabs with 2, except for the staircase to be loaded with 4. Okay? So you have here domestic, you have offices as well. So in case of offices, how much to be used, each and everything is mentioned here. You have as well areas where people will be gathering, like for example dining rooms, how much to be used, reading rooms without book storage to be 2.5, classrooms 3. Each and every specification has been mentioned here. So you should know how to use this particular code to get your life load. Nobody later on is going to give you your life load as well for you from where you will get it. Okay. So once again, these codes have been mentioned already for you. So by now, you should be able to draw the free body diagram for different elements, whether it's a slab or a beam. Okay. And then you should be knowing, you should practice on how to use these 2 codes which have been already uploaded for you. As I told you, whenever we are going to go and solve real problems in slabs and whatever, we are going to use these particular codes and we are going to have a good practice on them. Okay. So we learned to understand and read the drawings. After that, we learned how to shift the 3D drawings or the complicated drawings into simple drawings or simple free body diagram that we understand. After that, we should be loading these free body diagram. After that, we only can start the analysis. So the next step is going to be the analysis. And I have tried, since analysis is going to take a lot of time manually, whether you are going to go for moment distribution method or slope deflection, or you are going to go for the simplified method given by the code, it will take a lot of time. Just I wanted to highlight for you how to use them in a software, and hopefully we are going to do the comparison as well in this semester, although that it's short. So here, if you see, I have tried to highlight for you the analysis, which is showing you the internal forces. So this is from Tekla. Okay, so I have taken one column, and you can see now these are the loading on the column. Okay, this is let's say the n value on the column. So you can see at the top it's lesser. The bottom column is taking more load. Okay, so if you can see here, I don't know whether you will be able to see or not, but unfortunately, so just one second. Let me try to see what can be done. Okay, now I think it's better. You can see that it's 29.1 here, 59.2, because you can see that the column which is at the bottom is carrying the column which is at the top. That's why the value of n is increasing. And then we have, other than n, we have the bending moment diagram. Okay, so this is the bending moment diagram for the column. So whenever we are going to design the column later on, we need to design it for n value, which is the actual load, and then the bending moment, whether it's one bending moment or whether it's two bending moments, and we will see later on in this video. Okay, now most of the cases in reality are not going to be actually loaded. You have studied in design of structures 1 that we have actually loaded. We have actually loaded with uniaxial bending, with one bending, and then we have actually loaded with two direction bending, and we're going to see it. Okay, now most of the cases when it comes to reality are going to be actually loaded with uniaxial and actually loaded with biaxial, because normally we don't have symmetric arrangement of beams unless, for example, we are talking about parkings or we are talking about similar areas of shops, which is very rare. Okay. So this is the major bending moment, means in one direction. In the other direction, this is going to be the bending moment as well. Okay. Now for the beam as well, we can get the internal forces. Okay. So you can see here, we have, this is the loading on the beam. As you can see, we have either triangle or trapezoidal arrangement. Normally, we don't have it as UDL. Okay. In manual, to keep it simplified, we are converting it to be manual. I mean, to be rectangle. But the accurate thing to keep it as trapezoidal and triangle. This is the shear force diagram for this beam. This is the bending moment diagram for the beam, and this is going to be your deflection. So if you want, for example, if you want to design manually, then you can take these values from the analysis and design them directly. So I have m to be 13.1, and then directly I'll be using that equation of AS to calculate how much reinforcement is required. Okay. So this is for the beams, and then we are using another software. This is robot structural analysis. Okay, where I try to show you the bending moments for the beams and bending moments for the columns, since it's easier to be shown in terms of 3D for the column, or to show the both direction moments. Now you can see that this is going to be your bending moments going up, down, and it goes on. Now you can see this is the bending moment in the column that we are talking about. Okay. Now to keep it a bit simpler, I'm going to separate this column. Okay. Now if you can see, I have separated the column. This is one direction bending moment. This is the other direction bending moment. Now it will appear after normalization. Now you can see there are two directions. Now this direction, and then we have the other direction in that side. Now from where they came? From the beams. Now if you can see here, this particular column, let's see if we can zoom over there, or let me put it here. Now you can see this particular column is taking two beams. Now can you see that there is a beam from here and there is a beam from here? Now if we try to find the bending moment, if we try to take the bending moment, you will see that this beam is going to push this column to this side. Okay. So we have one bending moment going on this side. Let's just take the section shape, normalize. Okay, so you can see that this particular beam is pushing my column in this side. If I go to the other bending moment direction, I can see that this particular beam is pushing my column to the other direction. That's why this is acting as biaxial. What's the meaning of biaxial? It means we are going to have two moments in both directions. Now you can see if I take the column, you can see it bends in two directions. There is one because of this beam and there is one because of the other beam. Are we clear? Are we fine? Okay. Let us go to our video. Okay. So sufficient from the moments for the columns. This is the illustration that I told you about, showing the two direction bending moment, showing the reactions here. Okay, you can see that the reactions are shown. And these are the final drawings. We have ULS, we have SLS. ULS is the ultimate limit state, SLS is the service limit state, and we are going to take them into detail in the upcoming lectures. Okay. Now, if you see here, if we return back to the robot model, you have studied yield line analysis, right? Have you studied yield line analysis where your slabs are going to be divided into triangle trapezoidals, depending on one way and two way, depending whether it's going to be supported by 2 beams, 3 beams, 4 beams, and it goes on. It can be shown as well in the software, which will make it a bit easier for you. So if we try to see, this is going to be loading, then load distribution region. Now, can you see that this slab? Can you see that this slab is having 4 regions, 2 trapezoidal and 2 triangles, because it looks like a two-way with 2 different directions. Now, if we can see here, it's going to be 4 triangles. Why? Because we are having equal lengths of beams. Now, if I try to remove one beam, you will see that there will be 3 areas. Are you able to see that there are 3 areas? Now, if we are having, let's say I'm going to delete this one. I'm going to delete this column as well. Okay. You will see that we are going to have 2 areas. Half of the slab will be covered by this beam, half of the slab will be taken by the other beam as well. Now, if I remove this, removing this, for example, okay, still carried by the other beam. Or by the other slab. Okay. If we are taking it fully, so it will be like a cantilever. You can see that the full slab is taken by this particular beam. Okay, so this is the yield line analysis using different software. The last thing that we are going to cover today is going to be your design. So we are going to show you how we are going to use the software in order for us to compare our designs later, and how to understand the reinforcement. So once again, this is Tekla. Now you can see that almost all the elements are passing. We are going to generate the reinforcement so we can be able to see it, or we can visualize it. Okay. Now you can see after doing the analysis, the software will run your design. So here you can see that this is going to be the column reinforcement design for the full frame. This is going to be your cross section. This is going to be your other cross section of the column up, the upper level. And then finally, if you have another upper level, then you will be having the column with the reinforcement with the detail. Okay, the same thing can be done for the beam. Okay, so this is going to be the detailing for the reinforcement. It is showing you the labbing and the cross section of the beams for each and every interval, and it will give you as well the quantity takeoffs. Okay, so whenever we are going to start solving later on, we are going to compare and we are going to see how much the software are giving us compared to our calculation. We are going to use Excel a lot as well. Now, for certain elements where we don't have a lot of time to go and do the analysis, then I would recommend you to use simple software like, for example, SkyCIV. Okay, it's very easy for the analysis. So, for example, if I wanted to have a beam of 12 meters, then I'm going to apply a support, which is a pin support on the left side, and then another support on the right side, which is a ruler support, for example. Putting distributed load, like for example of 5. Now you can see that this is easy to be analyzed. You can use W square over 8 directly to get the values. But if we are having a complicated system, like for example, which is the case of real buildings. For example, if we have rather than having a roller support or a pin support here, I'm going to have a fixed support. So this is a fixed support, and then I'm going to have, rather than a roller, I'm going to have a fixed support here. I'm going to supply another pin support at the middle of 3. We have at 3, and then we have another support at 7, for example. And then instead of having distributed load, we are having variable load, for example, 3. Now, can you see that we are having different loading with different arrangements? The loading or the analysis of this particular system is not going to be something which is easy. Now, if you go on solve, now it will show you the reactions of this particular beam. It will show you the hand calculation if you are having the educational version. Okay. So this is going to be showing you how to calculate the reaction using the same method that you have studied in the college. Now it says for you that this is statically indeterminate. If it's statically indeterminate, then you should be using moment distribution method. And this is now going to be the moment distribution method for your system. Okay. So it says for you joint A is fixed, joint B is pinned, C is pinned, and then D is fixed. And then it's going to calculate for you the stiffness factors that you have done in theory of structures 1, coefficients. You are going to calculate fixed end moments, whatever you have done in the college. Okay. So rather than, especially in the projects, rather than going and doing the moment distribution method manually, you can take, or you can use different software to generate for you these things. And this is the moment distribution table, where you're doing the cross multiplication and you are getting the final bending moment values. Okay, and this is the reaction calculation. So these are the final calculation. Okay. So you can see that this is your reaction, or these are your reactions. This is your bending moment values. Now, after getting your bending moment values, you can go and design, whether you are using manual design or you are using Excel. Okay. So a lot of us are using, especially when it comes to beams and columns, we are using the software the full software, I mean, the big software to design them. But for slabs and foundation, we normally use basic Excel or basic software for the design. Okay. Another thing I can show you before closing up this particular lecture, you can see, for example, the reinforcement and how it's shown. Now you can see that the element, the beams that I have taken, or the beams that I had taken, are these two beams that were shown here. And whenever I start doing the design for them, you can see that this is how the bending moment will look like. Okay, so I'm just going to show the bending moment. So bending moment goes up, and then down, and then up, and then once again down, and then up at the support. This is going to be your beam reinforcement. This is how the reinforcement will be appearing. If you remember, we said we have top reinforcement, top bending moment here, bottom here, top here, and then we have top here, and then bottom here. So once again, top, bottom, and then up. Now what I can understand, top, wherever there is top bending moment, there should be top reinforcement. So you can see, because of the bending moment available here, and because of the top bending moment available here, we are showing our reinforcement. Okay, we are showing our reinforcement in the top, and then there is another main top which is located at the middle because of the bending moment. Now you can zoom in and check, and then we have the main bottom, which is going to be from the beginning till the end. This is my main bottom, which is resisting the bottom bending moment. And then we have assembly here, that's the hanger bar. Now you should know that the hanger bar is smaller in compared to the main bar. Okay, so you can see that the hanger bars are smaller than the main bars. Okay, smaller than the main top. And then finally we have the transverse, which are your links. Okay, so these are our links. And then you can see that whenever we are talking about the assembly top, there is a region. Can you see that there is a region where there is an interaction between the main top and then the hanger bars? This is whatever we call it as lapping area. Okay, area which is between these two. Okay. Can you see that the bar is going to the other side or entering into the area of the top bar? Okay. Doing that, we have finished our session. Once again, the session was an introductory session. It's meant to refresh your background data, so you will be ready for the design. So starting from the next class, we are going to start directly with the design of solid slabs. We are going to compare whatever we have done, whatever we are doing in manual design with the software to check whether we are getting the same results or not. Okay. Any questions before we finish this lecture? Any questions that you are having before finishing this particular lecture? And by the way, the attendance will be taken at any time, which will show when the students logged in and when they went out and then when they logged in once again. The handout is uploaded already. The PowerPoint for each and every chapter will be uploaded either before or after the session. Any further questions? Okay then. All the best.